Derive the velocity and orbital radius of an object along an elliptical path, part 3. Okay, so what we're going to do is we're going to have an object that's orbiting along an elliptical path, and we want to determine its velocity and its orbital radius at any point along that elliptical path. So what we're going to have to do is we're going to have to derive an equation for velocity and radius. Okay, here we have our ellipse right here, and we have our object, this blue point, that's orbiting around along this ellipse. And let's discuss all of these points on the ellipse. Okay, this is our focus. Our focus is where, let's say, the Earth is located, or the sun, or whatever massive body you're orbiting. But right now, let's just call this focus Q. Here we have our satellite. Our satellite moves from periapsis to some point D, okay? And so that's our satellite. We have A. A is our called apoapsis. A is the farthest point from the planet that we're orbiting. If our planet is that we're orbiting is Earth, we call this point A apogee. Point P, we call this periapsis. The closest planet, the closest point to the planet along the orbit. If this point at Q, if this object at Q is Earth, we call point P perigee. Okay, radius A. Radius A is the distance from point Q, the object that we're orbiting, point Q, to the furthest point on the ellipse, A, apoapsis. And this is called radius A. Radius P is the distance from point Q to P, periapsis. And this radius is called RP. Velocity at apoapsis. As this velocity moves around, as this object moves around the ellipse, the velocity V becomes tangential to the radius A at apoapsis. And it's not tangential, it becomes perpendicular to the radius A at apoapsis. And we call that velocity A. Velocity P is at periapsis, and it becomes, as the velocity moves from apoapsis around the ellipse and descends to periapsis, once it gets to periapsis point P, the velocity P becomes perpendicular to RP, radius RP. Our velocity vector V is tangent to the ellipse as it travels along the ellipse. From Q to our object is called RQ, the position vector. So from point Q to our object or spacecraft or whatever we call it, that's the position vector RQ. Angle beta is the angle between RQ, the vector position vector RQ, and the velocity of our spacecraft. We call that angle beta. The semi-major axis is B, from the center of the ellipse to the top of the ellipse. The semi-major, okay, I messed that up there. The semi-minor axis B is from the center of the ellipse to the top of the ellipse. The semi-major axis A is from the center of the ellipse to the periapsis, and from the center of the ellipse to apoapsis. And if you add those two together, the total length of the ellipse is 2a. Okay, that's it. Let's continue. Okay, what we intend to do is derive an equation that is in terms of the velocity v at point D up here. And point D is any point along here. I just show it right there, but it could be any point. So we're getting a velocity for any point along the ellipse. And to accomplish this, we will make use of the conservation of mechanical energy and the conservation of angular momentum. The conservation of mechanical energy at apoapsis and periapsis, point A and point P. We want the conservation of mechanical energy at these 2 points. So the kinetic energy at point A plus the potential energy at point A must be equal to the kinetic energy at point P plus the potential energy at point P. So the kinetic energy at A is equal to 1/2 the mass times velocity at A squared minus the gravitational constant g times the mass of the satellite times the mass of the planet that we're orbiting divided by the radius vector RA from Q to A. And that's equal to 1/2 the mass times mass of the satellite times the velocity at P squared minus the gravitational constant g times the mass of the satellite at P times the mass of the planet at Q divided by the radius vector from Q to P, which is RP, where the mass of the body at focus Q is MQ, MS equals mass of the satellite, RA equals distance from focus to the apoapsis, and RP equals distance from focus to periapsis. Let's continue. Here's our previous equation, which we derived for the mechanical energy from point A to point P. Now we need to use the conservation of angular momentum of the spacecraft at point A and at point P, about point Q. So we want to have angular momentum about point Q for A and P. And what is angular momentum? Well, angular momentum is the same property that keeps you upright on a motorcycle or a bicycle as the wheels turn. While you're riding down the highway or on a motorcycle or riding down the sidewalk or street on a bicycle, the bicycle stays upright. And the reason why it stays upright, it remains upright, is because of angular momentum. And you'll notice that as a motorcyclist comes to a stop, the motorcyclist has to put their feet down to stabilize that 800-pound motorcycle. Because if they don't, the motorcycle will tip over to one side or the other. But as the wheels begins to turn, the motorcyclist lifts their feet from the ground because angular momentum keeps the motorcycle upright. And that's what we're going to calculate here. The angular momentum of this object that's orbiting the mass at point Q. So let's call our angular momentum LQ. It's a vector. Angular momentum is a vector about point Q, right there. So angular momentum at apoapsis, right there, angular momentum is equal to RA cross the momentum. Well, cross is a vector symbol where we cross product, okay? So it's a vector cross product. And in order to know what that is, you'd have to take vector calculus. Okay, angular momentum at periapsis is equal to RQ is equal to RP cross P, momentum at P. Okay, that's a vector cross product. And now I'm going to show you what you need to know for vector cross product, so you don't have to worry about that. Okay, RA, as we know, is a position vector from Q to A, and RP is the position vector to the satellite at P from Q. RP from Q to P. Okay, let's continue. The conservation of angular momentum of the spacecraft at point P and Q about Q. Here's our angular momentum we derived last video. Velocity A is equal to the velocity of the satellite at apoapsis, that's VA, and velocity P is the velocity of the satellite at periapsis, which is VP. So these are the 2 points we're taking the angular momentum about Q. So what's the momentum vector at A is the momentum vector of the satellite at apoapsis is mass of the satellite times the velocity vector at A. And the momentum vector of P at P is equal to the momentum vector of the satellite at periapsis, which is MP. Let's continue. So here's a diagram I've drawn up so we can see what we're doing here. So what is the flight path angle? The flight path angle is the angle between local horizontal and velocity vector. So here's our flight path angle. Now, how do you find the flight path angle? Okay. Well, the flight path angle is the angle between the local horizontal and the velocity vector. Now, we know our velocity vector at all times is tangent to the ellipse. So how do we find this local horizontal here? Well, we know that our radius vector from point Q to the satellite, anywhere along the path, is called RQ. So our local horizontal is any line that is perpendicular to this radius vector, right there. That's that RQ, right here. And our local horizontal is perpendicular to that. Then from the local horizontal to the velocity vector is called the flight path angle. Okay. And our angle beta is the angle between the radius vector, which is up here, goes all the way up here, extended up here by this orange arrow, and then to the velocity is called beta, the angle between the radius vector and the velocity. Now, this flight path angle here, we're going to make use of that because this flight path angle, you'll see that LQ is equal to RQ times the velocity times the sine of beta. But that's also equal to RQ, right here, times the velocity times the cosine of gamma. And they're equal because these two angles are complementary angles. So the spacecraft flight, during the spacecraft flight, the flight path angle is 0 at periapsis. So right here, the flight path angle is 0, right here. From the local horizontal to the velocity, this angle between them is 0. The flight path angle is positive as the spacecraft rises to apoapsis. So it's the spacecraft is coming from periapsis, and it's considered to be rising towards apoapsis. And the flight path angle is positive. As you can see, the flight path angle is above the horizon. Okay, so RQ is increasing. So from Q going towards A, RQ is getting longer. Okay. The flight path angle is 0 again at apoapsis. So when the flight path, when the spacecraft gets to apoapsis, the flight path angle is 0. So the angle between the velocity and the local horizontal is 0. The flight path angle is negative as the spacecraft descends to periapsis. R is decreasing. So as the spacecraft leaves apoapsis A and ventures or descends towards periapsis, the flight path angle is negative as the spacecraft descends to periapsis. That means RQ is decreasing. Okay, let's continue. Here it is. I made another graph so we can see that. So as you can see, the angle between the velocity and the local horizontal is negative here because the velocity has dropped below the horizontal, okay? And RQ is decreasing. So the velocity vector has dropped below local horizontal. The flight path angle is negative as the spacecraft descends to periapsis. RQ is decreasing or getting smaller. Okay. Let's continue. Okay, let's look at a moving object around an elliptical orbit. Okay, here we have our elliptical orbit again. It's essentially the same diagram we had before. It's just that this one's going to move, and I'm going to see if I can kind of illustrate how this velocity vector moves around the ellipse. And I don't have velocity software, so I'm doing the best I can with this regular software. Okay, right here we have our flight path angle. And flight path angle is the angle between the local horizontal and the velocity. So here's the velocity, here's the local horizontal. Now, how do you find the local horizontal? Well, the local horizontal is a line that's perpendicular to the radius vector from Q to the spacecraft. So we find the RQ from Q to the spacecraft, then we draw a line that's perpendicular to that. And from that local horizontal, we travel to the velocity vector, and that's called the flight path angle, okay? Now, this other angle, beta, which is right here, is the angle between the radius vector and the velocity. That's the angle we use in our angular momentum, which we will call sine beta. Okay. And what we'll find is our angular momentum is equal to RQ, which is our radius vector, times V, which is velocity vector, times the sine of beta, the angle between those two. But gamma is equal to the flight path angle. And we see that the LQ, our angular momentum, RQ times V times the sine of beta, that's also equal to RQ times V times the cosine of the flight path angle. And the reason why those are true, that's true because these two angles are complementary angles. And we'll make use of that a little bit later. So what I want you to understand here is that what I said before previously is that the flight path angle is 0 at periapsis. That means the velocity and the local horizontal, the angle between those two are 0. As the spacecraft rises to apoapsis, you can see the velocity vector is above the local horizon, and our flight path angle is positive, okay? And then once the velocity gets to apoapsis, it becomes velocity VA and is perpendicular to the radius vector RA. And as the spacecraft moves or descends to periapsis, the flight path angle is negative. okay, as it descends to periapsis. And once the spacecraft gets to P, periapsis, the velocity vector and the local horizontal, the angle between those two is 0. So let's look at that and see what it does. Okay, I'm going to stop it here. Okay, as you can see, once we leave periapsis, the velocity vector is above the local horizon. Okay. And then as the velocity vector, as the spacecraft approaches apoapsis, as you can see, the angle between the velocity vector and the local horizontal is approaching 0. Okay, and it becomes 0, and then they're on top of each other. So therefore, this velocity becomes velocity A at apoapsis, and is perpendicular to the radius vector RA. Then as the spacecraft descends, it's called descending on the bottom side, as the spacecraft descends to periapsis, as you can see, the velocity vector has dropped below the local horizon, and therefore the velocity vector, the flight path angle is negative. The velocity vector is dropped below the local horizon, and the flight path angle is negative. And as the spacecraft approaches P, or periapsis, the velocity vector and the local horizon, the angle between those two, approaches 0, and they're on top of each other. And that velocity becomes velocity P. And velocity P is perpendicular to the radius vector RP, right there. Okay, let's continue. The magnitude of the angular momentum vector at apoapsis is about Q. So we're going to work here at A, apoapsis at A, angular momentum about Q. So our vector equation is equal to RA, the position vector at RA, cross the momentum vector at A, which is PA. Momentum at A is equal to mass of the satellite times the velocity vector at A. We factor out the mass of the satellite, and this cross product there is equal to the magnitude of the position vector times the magnitude of the velocity times sine beta. And I said sine beta is here, but as you saw in the previous video, when this velocity gets to A, it becomes velocity VA, and sine beta turns into 90 degrees because the velocity A is 90 degrees or perpendicular to the vector RA. So that's 90 degrees. Okay. So therefore, our angular momentum is equal to the mass of satellite times the magnitude of RA times the magnitude of velocity A times the sine of beta. And we know the sine of beta is 90 degrees. Let's continue. Okay, and if we do the same thing about Q at point P, okay, and it's the same equations, and we come out to our momentum about Q, angular momentum about Q is equal to mass of satellite times the magnitude of RP times the magnitude of VP times the sine of angle beta, and we know angle beta is 90 degrees at P. Let's continue. So therefore, they're equal to each other. And angle beta at apoapsis and periapsis is 90 degrees. And the sine of 90 degrees is 1. So we have these two equations equal to each other. We can cancel out the mass of the satellite. And we solve angular momentum for velocity at A is equal to velocity of A is equal to the RP times VP divided by RA. Now, if you remember some slides, previous slides we had the mechanical energy equation between A and P. Velocity A and velocity P. That was between A and P. We had RA and RP. But in this mechanical energy equation, we also have velocity of A, but it's squared. So we can plug those in. So we can plug velocity of A into this energy equation. Here's our previous equation. And we can cancel out the mass and multiply by 2. So the mass is in each one of these. So we can cancel that out and multiply by 2. And we rearrange our terms and solve for VP. VP is on both sides, so we bring VP over and solve for VP. Then we divide through by VP, and we invert and multiply. Okay. Now look at this term, RP minus RP squared minus RA squared. That's equal to RP minus RA times RP plus RA. And we plug that in, and lo and behold, we cancel one of those terms. RP minus RA divided by RP minus RA, and we cancel out one of these RAs in the bottom and the top, numerator and denominator. Okay. Now, we have this term. Here's our previous term right here. But look at RP plus RA. We can do something with RP plus RA, but first, let's find the mechanical energy between points D and P. Now, previously, you remember we had found the mechanical energy between apoapsis and periapsis. And that involved the radius vectors the vectors from RA and RP. Well, now we want to find the mechanical energy between points D and P. Well, the radius vector between Q and P is RP, and that remains the same. But for the radius vector between Q and D becomes different. It's RQ now. So we have the mechanical energy at D, which is the same as previously. The velocity to 1/2 the mass times velocity squared at D minus the gravitational constant G times the mass of the satellite times the mass of the planet at Q divided by RQ from Q to D. Okay, so that's the only difference between those two energy equations. So we multiply by 2 and cancel masses as we did previously. Okay, and we solve for V. Now we have V squared equals VP squared plus 2G times MQ divided by RQ minus 2G MQ divided by RP. Let's continue. So now previously we have our previous equation, energy equation between D and P, periapsis. And we have our energy equation between apoapsis and periapsis. These two equations. If you look at them, we have VP squared is equal to this quantity on the right. Well, we can plug that into our energy equation between D and periapsis. Okay, so we plug in. All right, take this equation and plug into that one. Okay. Now, that RP plus RA, which I mentioned previously, we rearrange in terms. RP plus RA equals 2A, so we plug that in. Okay. And so now we have RP over here, 1 over RP here, and RA divided by 2A RP. Well, we make those same, we multiply the denominator and the numerator and denominator by 2A, and we get the same denominator, and we can add those points. We can add the numerators and under the same denominator. Let's continue. Okay, so here's our previous equation. And we add the numerators. And RA minus 2A is here. RA plus RP equals 2A, and we bring 2A to the left-hand side. So we have RA minus 2A equals minus RP, and we plug that into there. And we multiply by 2, and now we got RP's canceled and the 2's canceled. So canceling terms, and our final velocity equation is equal to the square root of the gravitational constant, G, times the mass of the body that we're orbiting at Q, times the quantity 2 divided by RQ minus RA, 1 over RA. So here's our previous equation for our velocity. But what is the value of RQ? Well, we haven't determined that yet, but we did in a previous video. Kepler's famous equation, part 3, we determined R. And here it is. This is our RQ. This is our Q. Our R to the satellite is RQ. So R, we determined here, was equal to A times the quantity 1 minus epsilon, small e, times cosine of big E. And cosine of capital E is equal to the quantity small e plus cosine theta divided by 1 plus small e times cosine theta, where R is equal to RQ. And angle E, the capital E, right there, is equal to the eccentric anomaly. This is the angle E, the eccentric anomaly. Small e is equal to the eccentricity, and theta, angle theta, is equal to the true anomaly. So if we take those values and we plug in, we get RQ is equal to A minus eccentricity times A, which is A is the semi-major axis, times that quantity in red. Okay, we plug in and multiply and make the same, get the same denominators under these two fractions, and then we add the numerators, and we see the terms in red cancel, and we get RQ equals A minus A times eccentricity squared divided by 1 plus eccentricity times the cosine of theta. Here's our previous equation. Factoring out A, we get our final equation for radius. RQ is equal to the semi-major axis A times 1 minus the eccentricity squared divided by 1 plus eccentricity times the cosine of theta. And the final equation for our velocity is equal to the square root of gravitational constant G times the mass of the body at Q times the quantity 2 divided by RQ minus 1 over A, which is the semi-major axis. So therefore, to find the velocity at any point in orbit, we can find the radius at any point in orbit because we get the cosine of the true anomaly to find the radius. And then we plug this radius into this velocity equation, and we get the velocity. A is equal to semi-major axis, and angle theta is equal to true anomaly. And that's it. There was a lot of calculation we went through for that, but it's going to come in handy in our final video. Well, we derived the velocity and orbital radius of an object along an elliptical path. In part 4 of the next video, we will derive the total mechanical energy of an elliptical path. You'll see why you need this. That's going to be a very good example problem, and you'll see why we need that. Okay? I enjoy making this video. It's not magic, it's the law. Until next time.